Welcome to Python Machine Learning Projects, a video course by Pact Publishing. I am Alistair Ruane, and I'm going to be the author, Alexander T. Combs' voice for this course. Alexander T. Combs is an experienced data scientist, strategist, and developer with a background in financial data extraction, natural language processing and generation, and quantitative and statistical modeling. He is currently a full-time lead instructor for Data Science Immersive Program in New York City. Now let's talk about machine learning. Machine learning is rapidly becoming a fixture in our data-driven world. It is relied upon in fields as diverse as robotics and medicine to retail and publishing. In this course, you will learn how to build real-world machine learning applications step by step. Working through easy-to-understand projects, you will learn how to process various types of data and how and when to apply different machine learning techniques such as supervised or unsupervised learning. So let's know more about our course. We will first build an application that monitors prices continuously. Our app will generate an alert once an anomalous price appears. We will then build an application for prediction in the IPO market. In the next section, we will build a system which generates a daily newsletter which will be saved in our feed. We will then use machine learning in stock market predictions and devise our very own trading strategy. Following this, we will construct an image-based deep learning algorithm. Lastly, we will build a chatbot based upon previous chatbot studies and research. By the end of the course, you will have learned to apply various machine learning algorithms and will have mastered Python's packages and libraries to facilitate computation. You will be able to implement your own machine learning models after taking this course. All you need is Python 3.x and a desire to build real-world machine learning projects. You can refer to the detailed software list provided along with the code files of this course. This course is for Python programmers, data scientists, and architects with a good knowledge of data science, and all those who want to build complete Python-based machine learning systems. So that was a brief overview. Now let's dive into the course together. See you there. Hello, welcome to a brand new section of the course. Build an app to find cheap airfares. In this section, we will have a look at these topics. First, we will start with sourcing airfare pricing on the web. Then, we will retrieve fare data using advanced web scraping techniques. We will also extract prices from the document object model. We will then identify outlier fares with clustering techniques and send real-time alerts with IFTTT. Now we move on to the sourcing airfare pricing data. In this video, we will look at the source from where airfare pricing data is obtained. Let's talk about mistakes. They're a part of life. Everyone makes them, even airlines. In the super-secretive society of travel hackers and mileage junkies, it's well known that airlines occasionally and accidentally post fares that exclude fuel surcharges. Remarkably, this isn't the only type of mistake that they make. You might expect that advanced algorithms would be updating fares for each flight, taking into account an enormous number of factors. For the most part, you'd be right. However, due to legacy systems and the complexity of dealing with multiple carriers and multiple jurisdictions, mistakes do occur. Now that you know these fares exist, how can you get in on them? Machine learning, of course. As they typically last just a few hours before they disappear, we're going to build an application that continually monitors fare pricing. Once an anomalous price appears, our app will generate an alert that we can quickly act on. So let's get started. Fortunately, airfare pricing data is easier to obtain than real estate data, so it isn't hard to find. There are both free and paid API sources, as well as numerous websites that provide the data. I tested a number of these services, but in the end, there was only one that provided the data in a workable format. This format made it super simple to find the lowest priced flights months in advance. Before I tell you which service it is, let me show you the typical flight search interface. So at this site, you can see that the problem with this type of interface for our purposes, and all the APIs have the same fields, is that we would need to run queries for all the dates that we're interested in for every possible trip length for each airport. While possible, it is ugly and it would take far too much effort. Fortunately, there is a better way. There is a little-known tool that Google provides called the Flight Explorer. This is the site where you can see the tool. This tool lets you view the lowest cost fares from one region to another over a period of months. Here is an example of a search for 8 to 12-day trips from New York to Europe. The cities are returned sorted in order of price, the lowest cost to highest. You can see that here. This format is ideal to find mistake fares as the results are returned sorted by price for an entire region over a 60-day period. This ensures that the outlier fares surface to the top when they occur. That's the good news. The bad news is that Google has made pulling down this data programmatically quite challenging. Fortunately, with a bit of clever coding, we can still get the data that we need. So in this video, we have sourced the airfare pricing data successfully. Awesome! In the next video, we will retrieve the fare data with advanced web scraping techniques. Welcome to another video in this section, retrieving the fare data with advanced web scraping techniques. In the previous video, we learnt the source of airfare pricing data. In this video, we will perform the steps which will enable us in retrieving fare data with web scraping. In Python, there are a number of Python-based libraries, example, Beautiful Soup, Requests, and Scrap for web scraping. The page that we want to scrape is entirely AJAX-based. Asynchronous JavaScript AJAX is a method to retrieve data from a server without having to reload the page. What this means for us is that we'll need to use a browser to retrieve the data. While this might sound like it would require an enormous amount of overhead, there are two libraries that, when used together, make it a lightweight task. The two libraries are Selenium and Phantom.js. Selenium is a powerful tool to automate web browsers, and Phantom.js is a browser. Why use Phantom.js rather than Firefox or Chrome? Phantom.js is what's known as a headless browser. This means that it has no UI. This keeps it lean, making it ideal for what we're trying to do. To install Phantom.js, you can download the binaries or source from this site. We'll also need another library called Beautiful Soup 4 to pass the data from the page. If you don't have this installed, you should pip install this as well. Let's see if we have installed it or not. We go to CMD. We will first install the Selenium. The requirement is already satisfied because I have already installed it here. Next, we will check for Beautiful Soup 4. Here that is installed too. If it is not installed, you will have to install it using the command pip install. With this done, let's get started. We'll start out working the Jupyter notebook. Jupyter works best for exploratory analysis. Later, when we've completed our exploration, we'll move on to working in a text editor. Text editors are better for writing code that we want to deploy as an app. To deploy the notebook, we have to give this command. So this will start the notebook in the browser. You can click on New as we are using Python default. And a new notebook is created here. You can rename the file name. First, we will import the libraries. We need to import Panda and NumPy. You can click on Run here. So the star means it is being run. There is no error. Next, you need to import the WebDriver. This is the code for that. Again, it is run successfully. Next, you need to run Beautiful Soup. And then we will install the matplotlib. Next, we'll set up the code to instantiate the browser object. This is the object that will pull down the page for us. You can select the airports or regions that you like by running a search in your browser and copying the URL. Here, I am searching for trips between New York airports and several cities in Asia. This is the code for that. You can select the from and to destination and number of days you are traveling. Then we copy this URL and place it in the code so that it will fetch data from the site. We need to send the receiving server as a user agent. You can use the agent I listed here, or you can swap this out for your own agent if you prefer. It becomes important when we get to the parsing stage. If you are using one agent to select Document Object Model (DOM) elements in your normal browser and then passing a different agent in your code, you may end up with problems passing the page, as the DOM can be user agent dependent. You can find your user agent just by running a Google search for what is my user agent. So when you type what is my user agent and search for it, you will get your information here. You can click on that. This is your user agent. Now just copy this and paste it here. Copy this information and then use it in the preceding code if you plan on using this for other scrapers. Then you have to run the code. You can see that it is being run. There are no errors. Once the preceding code has been run, you can use the following line to save a screenshot of the page. Check it to make sure that everything looks good. For that, you run this line. If all goes as planned, you should see true as the output and have a file with the image of the page that you scraped. It should look just like the page in your normal web browser. This is the page we have taken the data from. I have opened the Windows Photo Viewer and it looks exactly the same. Excellent! In this video, we have learned to retrieve data from web using web scraping. In the next video, we'll move on to parsing the page to extract the pricing information. Welcome to a new video in this section, parsing the DOM to extract pricing data. Previously, we have retrieved the fare data using web scraping techniques. In this video, we're going to take a look at how to obtain information about pricing data from DOM. We will look at different values like prices, best fares, cheapest fares, etc. We will then identify outliers using clustering techniques. The DOM is a collection of elements that form the structure of a web page. If you have ever viewed the source of a web page, you have seen the components of the DOM. They include elements and tags such as body, div, class, and ID. We'll need to work with these elements to extract the data we need. Let's take a look at the DOM for our Google page. To see it, right-click on the page and click on Inspect Element. This should be the same for Firefox or Chrome. This will open the Developer tab that allows you to see the page source information. You can see the elements here. Once this is open, choose the element selector in the upper left corner and click on one of the price bars to jump to that element. When we click on 329, we get information on that element. The first thing you are likely to notice is that there isn't any pricing data in the div tags. If you hover over the bars, a tooltip will display the fare, but this is all done with JavaScript and is not available with the DOM. In fact, the only thing available is the height of the bar that represents the fare. So how can we get data that isn't there? We deduce it. The page does give us just enough clues to infer the price using the height of the bars. You'll notice that the one fare listed for each city is the best fare. You can see it to the left-hand side of the bar graph. This div provides you with the pricing as text, as shown here. So click on 329 and see the pricing. You will also notice that each city has a bar that matches the lowest fare. It's highlighted in a darker shade than the other bars, as it has a unique class that generates this coloring. We can find it. Once we find it, we can use its height divided by its price to determine the price per pixel. Using this, it becomes a simple exercise to derive the price for each flight. Let's code this now. The first step is to feed the page source to Beautiful Soup, so we do that. We can then retrieve a list of all the best prices, so we code for that. This is the div tab we are using from here. You can just copy and paste it. When we run it, we get the list of best prices. As the city with the cheapest fare rises to the top, we can just use it. The best price can be viewed using this command. So 329 is the best price. Next, we'll get the list of bar heights for each. So this is the code for that. We have taken the div tab from here. Clicking on 329 and Inspect Element, we have to copy and paste it. Then we run it. Again, we only need the first one. As we had done for the prices, we will do for the heights. The best height is 30.32. Then we can calculate the price per pixel of the height. That is, we need to divide the best price by best height. So the price per pixel is 10.84. Next, we'll retrieve the bar heights for all flights in each city. Let's view what is there in the cities. You need to change just this. Now you can see that the cities variable contains the overall cities in the page. It retrieves the bar heights for all the flights. Then we run the code for that. Now let's calculate the fare. Let's view what is stored in the fare. You can see the list of fares for all the flights. This completed, we now have a data frame with the cheapest fare for a 2-month period. Let's take a look. We calculate the minimum fare using fares.min function. You can see that 329 is the minimum fare. Our minimum fare should match with the one we can see in the list. So here, 329 is the minimum fare in the list. The code generates this output. Our minimum fare should match the one that we see on the page, and it does. Let's now take a look at the full list. Everything looks good. We can now move on to setting up our outlier detection. Also, you can calculate the median of fare using fares.median function. You can see 428 as median fare. Or you can get all the statistical values using this command. You can get the values of count, mean, STD, min, and max of the list. Airfares are updated continually throughout the day. If we're trying to identify fares that are priced well below what they should be priced, how might we do this without machine learning? It seems like it would be fairly simple, but when you start to consider the options available, it quickly becomes far more complex than anticipated. One option would be to get the prices for every city and set a threshold so that if they fell below that price, you would trigger an alert. This might work, but do you set a percentage alert below the currently lowest price? A strict dollar level trigger? Then where exactly do you place it? What if fares naturally decline due to seasonal factors? Maybe you could check each bar for deviation from the median bar. What if prices are nearly flat and there is a minor drop? Maybe check each bar's height versus its neighbouring bars. What if the mistake fare occurs across more than just one day? As you can see, it's not as simple as it might appear. Given that, how do we avoid the headaches of storing pricing data for each city, dealing with seasonality, and trying to set thresholds? We use a clustering algorithm instead. There are a number of clustering algorithms available, but for the type of data that we are working with here, we will use an algorithm known as density-based spatial clustering of applications with noise, dbScan. It is an exceedingly effective algorithm that tends to identify clusters of points the same way that humans do. The following image is a visualization taken from a Skykit Learns documentation. It demonstrates dbScan's effectiveness across a range of different data distributions. As you can see, it is quite powerful. Let's now discuss how the algorithm works. To understand the dbScan algorithm, first, we need to discuss two parameters that must be set for the algorithm to work. The first parameter is called epsilon. This parameter determines the distance 2 points can be from each other and still be in the same cluster. If epsilon is large, then any 2 points are more likely to cluster together. The second parameter is called min points. This is the minimum number of points, including the current point, that are required to create a cluster. If min points are 1, then every point will be 1 in a cluster. If min points are greater than 1, then it's possible for some points to not be affiliated with any cluster. These then become the noise, the N, in dbScan. The dbScan algorithm proceeds as follows. Randomly select a point from the set of all points. Search epsilon distance in all directions from this point. If min points are within this epsilon distance, all points within the epsilon become affiliated with a cluster. Repeat the procedure by checking all the new points that were added to the cluster. Continue this until no new points can be added to this current cluster. When this occurs, the first cluster is complete. Now begin again by randomly selecting a new point outside the closed cluster. repeats this same procedure until no new clusters can be formed. Now we have an understanding of how the algorithm works, let's apply it to the airfare data. We'll begin by creating a simple graph of the fares to inspect. This is the code for that. You can see the plot here. We can see that fares flatline for a number of weeks and then begin to rise dramatically. Most people would likely see this as 4 major clusters. Let's now set up our code to identify and display the clusters. First, we will set up a price frame that we can pass to the dbScan object. So this is me setting a price frame. Then we'll need to import a couple of libraries for the clustering. So here we are importing libraries dbScan and standard scalar. Finally, the following code will apply the dbScan algorithm to our fare data and output a visualization. So you need to run this code. Let's unpack this line by line. In the first line, we are utilizing standard scalar. This object will take our data, subtract the mean from each point, and divide each by the standard deviation. This step gets all of our data on the same basis and readies it for the algorithm. The standardized data is then passed to the dbScan object. Here we are setting the 2 parameters that we discussed earlier. We set EPS, or our epsilon distance, equal to 0.5, and set min samples to 1. The next line sets labels equal to the array of the labels output from the algorithm. Every point, as min points is set to 1, will be associated with a cluster ID. These clusters will be labeled from 0 to n-1, where n is the total number of clusters. The next 2 lines get the total number of clusters and their unique labels, and the line that begins with colors generates a color map for our graph. The remainder of the code then sets up our graph by applying a unique color to each cluster and setting a title for the graph with the total number of clusters. Let's take a look at the output for our fare data. As you can see, the algorithm has identified distinct clusters, which is exactly what we had hoped for. Now, having just told you how well it worked with these parameters, I'm going to suggest changing them. Why mess with perfection? Well, let's take a look at a few scenarios in which we introduce artificial fares. With our current fare series and the same parameters, let's introduce a new fare into the mix. We'll begin by replacing data point number 10 in our series. So let's see what is the value at 10. Value at 10 is 540. We'll change it. We will make a function called testClusters, which contains the same steps as we have discussed before, so it will be easy for us to run the same line of code again and again in a cluster. So we change the value to 500. I have passed the data series, that is px. The epsilon value is 0.5. The swap index is 10, that is, we are changing the 10th position. So you will see that it becomes its own cluster near the bottom. Now let's increase our epsilon parameter, as we are only clustering 2 groups. We now keep the same dummy fare, but increase the epsilon to 1. You can see 2 clusters are formed here. You can see that we now have 2 clusters. Our $500 fare has been placed in the main cluster, and the fare at the far right-hand side at the top of the graph has been placed in its own cluster. This looks reasonable as the far left side fare is a clear outlier. Let's test this a bit more. How far would we need to drop our dummy fare to have it in its own cluster? This illustrates the results of dropping the dummy fare further. Dropping it to 400, we can see that it is still a part of the primary cluster. Dropping it to 300 also gives 2 clusters. So then we change the epsilon value to 1.5, few other scenarios using other cities. This is the Tokyo Narita Airport series. We have a single cluster, which is what we'd hope. Let's swap in a dummy fare now. We'll swap fare 45 in the series. Let's see the value of fare 45. We'll move it from 401 to 300. This is a major decline, far more than the $100 decline that triggered our new cluster in the other series. but it is clearly within the range of typical prices, so we wouldn't want a new cluster to form. You can see that it didn't. Why is this the case if there is such a large distance between our dummy fare and the two fares to its left and right? This is because we are working with the entire series and not just the immediate neighbours for each point. Most likely, our dummy data point was recruited to the cluster by the points to its left. Let's try one more scenario. We'll swap a fare out to the right, further from our lower left cluster. Here we have swapped fare number 55. The value at 55 is approximately 400. We will change it from 400 to 200. This resulted in a new cluster. The fare is within the range of the other fares in the full series, but it is certainly an outlier at this point. We most likely don't want to be alerted to it, however. As we don't want to be alerted every time there is more than a single cluster, we need to set up rules for the scenarios where we do want to be alerted. First, as we are looking for mistake fares, we expect them to be equal to the lowest price displayed. We can group by cluster and retrieve the minimum price using the following code. It generates this output. Then we will aggregate by cluster and display the minimum price and count. The code generates the following output. We also expect that the mistake cluster will be smaller than the main cluster. We'll set a limit on the size of our mistake cluster by requiring it to be less than the 10th percentile for the count. In this case, it will be less than 7 fares. This figure will vary depending on the number and size of clusters, but this should be a workable figure. To see the quantile breakdown, you can use this line of code. The output will be something like this. Let's add one more condition. Let's set a minimum distance between the lowest priced cluster and the second lowest priced. Doing so will prevent a scenario like the one seen in this output. Here the fare is the lowest, but it is just above the range of the other cluster. Setting a minimum distance will cut down the false alerts that we receive. Let's set it at $100 initially. In this video, we have learnt to obtain information from a DOM by parsing it. Excellent! In the next video, let's move on to how we can put it all together with a real-time fare alert app using IFTTT. Hi, this is another video of this section, sending real-time alerts using IFTTT. Previously, we parsed the DOM to extract pricing data. In this video, we're going to take a look at sending real-time alerts using IFTTT. To have a chance at getting these cheap fares, we're going to need to know in near real time when they happen. To accomplish this, we'll use a service called If This Then That, IFTTT. This is a free service that allows you to connect a huge number of services together with a series of triggers and actions. Want to save all the pictures that you've liked on Instagram to your iPhone photos? Want to get an email every time a particular person tweets? Want your Facebook updates posted to Twitter? IFTTT does all of these and more. To get started with IFTTT, sign up for an account at ifttt.com. Sign up for the Maker channel at this link. Sign up for the SMS channel at this link. The Maker channel allows HTTP requests to be sent and received, and the SMS channel does the same for SMS messages. Once you've created an account and activated the two channels, click on My Applets from the homepage, then click on New Applet. You will get an interface like this if you click on the plus sign. Then search for and select the Maker channel. Next, select Receive a Web Request. Click on Connect. Then we'll create an event called Fare Alert. Click on Receive a Web Request. Write the event name and click on the Trigger button. Next, we'll set up the that. So click on this plus sign, select SMS and click on Send me an SMS. You will get a screen like this. After this, we'll fill in the field with Fare Alert. make sure to replace the curly braces. Once this is complete, you can customize your message with the city and airfare. You can add ingredient in the message. You can write this text. You can select city as value 1 and fare as value 2. Then click on Create Action. You will see this screen. Turn on the notifications and click on Finish. To test the setup, go to this site. To get the trigger information, click on Settings. You can see the URL here. Go to the URL. Then fill in Fare Alert for event and place the test city and fare in the value 1 and value 2 boxes. Say NRT and value as 400. Finally, click on Test It, and you should receive a text message in just a few seconds. In this video, we have sent real-time alerts using IFTTT successfully. Amazing! Now that we have all the pieces in place, we will pull it all together into a single script that will monitor fares 24/7 in the next video. Hi, and welcome to the last video of this section, putting it all together. In the previous video, we saw how to send real-time alerts to our system using IFTTT. In this video, we're going to put together our entire project part by part and check if it's built successfully. Up until this point, we've worked in the Jupyter Notebook, but now to deploy our app, we'll move to working in a text editor. The Notebook is excellent for exploratory analysis and visualization, but running a background job is best done with a simple .py file. So let's get started. We'll begin with our imports. You may need to pip install a few of these if you don't already have them installed. Next, we'll create a function that pulls down the data and runs our clustering algorithm. We have created a check flights function. Notice that we're including an explicit wait when we retrieve our data. As the page has an AJAX request, we need to add this wait time to ensure that the page's pricing data has been returned before we move on. If the scraping still fails for some reason, we'll send a text noting this failure. This is the complete part used for this work. Now we'll check whether our rules have triggered. If yes, we'll send a request to receive a text. So here, in out.request.post, we need to add the secret key that we have created in ifttt.com maker. You can just copy the key from here and paste it there. We are assigning value 1 as script and value 2 as failed. Next, we need to set our scheduler to run every 60 minutes. That should do it. We can now save this as farealerter.py and run it from the command line. It will continue running and check fares every 60 minutes. If a mistake fare occurs, we'll be one of the first to know. We have added a print command here to know if it is successfully running. Let's go to the command prompt. You can see it is successfully built. Note that this is a minimum implementation of this code. To create a proper implementation, good logging practices should be put in place in lieu of print statements shown here. For more information on how to implement logging, have a look at this tutorial. In this video, we put together our project and successfully built it. Awesome! We've covered a lot of ground in this section. We've learned how to find the best airfare data on the web, how to work with the DOM to find and parse the HTML elements, how to cluster data into meaningful groups, and finally, how to send text alerts from code using web requests in IFTTT. While what we've covered here is for airfares, nearly everything that we've done could be reused for any type of pricing you'd like to be alerted to. If you do decide to use it for airfares, though, I hope it provides you with many happy travels. In the next section, we'll cover how to use classification algorithms to help predict the IPO market. Hi, and welcome to the section Forecast the IPO Market using Logistic Regression. In this section, we'll take a closer look at the IPO market. We'll see how we can use machine learning to help us decide which IPOs are worth a closer look and which ones we may want to take a pass on. We will learn about data cleansing and feature engineering. Then we will move on to binary classification with logistic regression. We will also perform model evaluation and discuss about feature importance. Now we move on to the first video of the section, the IPO market. In this video, we will first study about the IPO. We will look at the recent IPO market performance and devise a baseline IPO strategy. In the late 1990s, getting in on the right IPO was like winning the lottery. First-day returns for some technology companies were many times their initial offering price. If you were lucky enough to get in an allocation, you were in for a windfall. Here are a few of the top first-day performers from the period: VA Linux, Globe.com, Foundry Networks. While the days of dot-com mania are far behind us, IPOs can still have outsized first-day returns. Here are just a few that have risen over 100% on their first day of trading in the past year: Ceres Therapeutics, Aldro Biotech, Shake Shack. As you can see, this is still a market worth paying attention to. Before we jump in and begin modeling, let's first discuss what an IPO or initial public offering is and what the research tells us about this market. After that, we'll discuss a number of strategies that we can apply. An initial public offering is the process whereby a private company becomes a public company. Public offerings raise capital for the company and give the general public an opportunity to invest in the company by buying its shares. Though there are variations in how this occurs, in the typical offering, a company enlists the aid of one or more investment banks to underwrite their offering. This means that the banks make a guarantee to the company that they will purchase all of the shares being offered at the IPO price on the day of the offering. The underwriters, of course, do not intend to keep all of the shares themselves. With the help of the offering company, they go on what's called a roadshow to drum up interest from the institutional clients. These clients put in a subscription for the shares, which indicates their interest in buying the shares on the day of the IPO. This is a non-binding contract, since the price of the offering is not finalized until the day of the IPO. The underwriter will then set the offer price, given the level of interest expressed. What is interesting from our perspective is that research has consistently shown a systematic underpricing of IPOs. There are a number of theories for why this happens, and why the level of underpricing seems to vary over time. But suffice it to say, studies have shown billions of dollars are left on the table every year. In an IPO, money left on the table is the difference between the offering price of the shares and the first day's closing price. One other point that should be mentioned before we move on is the difference between the offering price and the opening price. While you can occasionally get in on the deal through your broker and receive the IPO at its offering price, in nearly all instances, you, as a member of the general public, will have to purchase the IPO at the typically higher opening price. We'll build our models under this assumption. Recent IPO performance. Let's now take a look at the performance of the IPO market. We're going to pull down data from IPOscoop.com. This is a service that provides ratings for upcoming IPOs. Go to www.iposcoop.com. Go to the button at the bottom of the page to download the spreadsheet. We'll load this into a Pandas and run a number of visualizations using our Jupyter notebook. Here your spreadsheet is downloaded. You can then rename it as IPO data. Change the type to comma-separated values file. That is our .csv file. This path is supposed to be copied and switched on Jupyter. Create a new Jupyter notebook. First, we'll set up the imports that we'll need through the section. These are the necessary imports. Then we'll pull in the data. Here you have to copy the path of the CSV file that we copied earlier. You can see the output here. Here we can see that we have some great information on each IPO: the offering date, issuer, offering price, opening price, and price changes. Let's first explore the performance data by year. We'll first need to perform some cleanup to properly format the columns. We'll get rid of the dollar signs and the percentage marks. Here you can see that the percentage and dollar signs are replaced by a tab or space. You can see the output here. You can see that the dollar and percentage sign is not seen anymore. Next, we'll fix the data types for the columns. They are all objects currently, and we want numeric types for the aggregations and manipulations that we will perform. This is the information of the data. There are some NC values in our data that we'll need to replace first. After this, we can change the data types. This line will replace the NC values by 0. Then we are changing the data type of each column. Note that this throws an error, out of bounds date time. This means that one of our dates is not properly formatted. We find this based on the previous stack trace and fix it. Now you can see here that the date is of the type 120 by 11. Let's fix it. After fixing the error, we will observe the error is ATB 908th cell. The proper date is 11/20/2012, so we'll set it and rerun the preceding data type fixes. After that, everything should go smoothly. We will replace the cell number in this command and run it. So our date is fixed. Once it is done, we will rerun our previous code. Let's see what has changed. The data types have changed here. Now, finally, we can start our exploration. Let's start with average first day percentage gain. We group the percentage gain by date. You will see a graph here. These are some healthy percentages in recent years. Let's now take a look at how the median compares to the mean. This is the code you run. You can see the plot here. From this, we can clearly see that the distribution of returns is skewed by some large outliers. Let's now take a look at them. The output shows us statistics of the first day percentage change, where it calculates all parameters at the implementation of one function, describe. Now we can plot it as well. Here is our histogram. From this, we can see that most returns cluster around 0, but there is a long tail to the right with a number of true home run offerings. We've looked at the first day percentage change, which is the offering price to the closing price. But as we noted earlier, there is very little chance of getting in on the offering price. Since that's the case, let's now look at the returns for the opening price to the closing price. Do all the gains go to those who get in on the offering? Or is there still an opportunity to jump in and capture an outsized return on the first day? To answer this, we'll first create two new columns that are dollar change open to close and percentage change open to close. Change open to close is the difference between the close and the opening price, and the percentage is calculating the percentage of the dollar change open to close. Once it is done, we will print using IPOS function. Next, we'll generate our statistics. Immediately, this looks suspect. While IPOs can fall after their opening, a drop of nearly 106% seems unrealistic. After some investigation, it looks like the two worst performers were in fact bad data points. This is just a fact of life when working with real-world data, so we'll correct these and regenerate our data. So this is the code for that. Here, I have used the min value as my limit. You can see here that we need to change the 250th value. You can change the data point using ipos.lock. Now we need to change the second bad data point. We will just half the min value. The second bad data point is 1868. Run the same code again. Once this is done, you can calculate the statistics once again. You can see the min value here. This is down to a 50% loss, and it still looks suspect, but after taking a closer look, it was the Zillow IPO. Zillow opened extremely hot, but quickly came back to Earth before the closing bell. This tells us we appear to have cleaned out our bad data points. We'll move forward now and hope that we have cleaned up the bulk of the errors. So we will create our histogram again. It's a perfect histogram. Finally, we can see the shape of the distribution for opening to closing prices, compared to the distribution of offering to closing prices. There are notable differences. Both the mean and the median have fallen considerably, and the bars immediately to the right of 0 look like they've had a healthy shave, while the ones to the left seem to have grown in equal proportion. Note that the long tail on the right-hand side is less pronounced, but still evident, so there is a glimmer of hope. Now let's talk about the baseline IPO strategy. Now that we have a sense of the market, let's explore a few strategies. How would we fare if we were to purchase every IPO at its opening price and sell it at the close? We'll take a look at the 2015 year-to-date data, and you can see the statistics here. Next, we will see the sum of the data. You can see the sum is 36.46. Let's also break out the winning trades and losing trades. First, winning. You can see that the min value is nearly 0. Now we will see the same for losing trades. You can see that the min value is -6. So we see that if we invested in every IPO this year, we would have been quite busy investing in 250 IPOs, with about half making us money and half losing us money. On the whole, this would have been profitable, as the gains from our winning IPOs would have ended up covering our losses and then a bit. This, of course, assumes that there are no slippage or commission costs, which there inevitably are in the real world. However, this is clearly not a golden ticket to riches, with a mean percentage return of less than 1%. Slippage is the difference between your attempted entry or exit price for a target stock and the price at which your order is actually fulfilled. Let's see if we can use machine learning to help improve our results from a naive approach. A reasonable strategy would seem to be targeting that long right tail, so we'll focus on that. So in this video, we have done a detailed study about the IPO market. Very good. In the next video, we will perform feature engineering. Hello. This is the second video of the section, Feature Engineering. In the previous video, we studied the IPO market. In this video, we will add, correct, and change features of IPO as per our requirement. What might impact the performance of an offering as it begins trading? Perhaps the recent performance of the market in general, or the prestige of the underwriters could impact it. Perhaps the day of the week or the month that it trades is important. The consideration and inclusion of these factors in a model is called feature engineering, and modeling this is nearly as important as the data that you use to build the model. If your features aren't informative, your model simply won't have value. Let's begin this process by adding a few features that we expect may influence the performance of an IPO. We'll begin by retrieving data for the S&P 500 index. This is perhaps the best proxy for the general US market. We can download this from Yahoo Finance at finance.yahoo.com. So you can set the date from 3rd of January 2000 to current date and click on Apply. Once you do that, you can download the CSV file and use it to further process. We can then import the data using pandas. We will load the data using this code. Here is the path of the file, which we have downloaded from finance.yahoo.com. You can see the data here. Because broad market performance over the past week would be a logical influence on a stock, let's add this to our data frame. We'll take the closing price of the S&P 500 yesterday as a percent of its close 7 days ago. So, we will create a function for that. Here we are calculating the last 7 days' performance. Next, we need to get the week change. You can see the error in 4 dates. It gives us several dates that fail, which tells us that our IPO dates may have a few errors. Checking the IPOs that have these dates indicates that they are off, so let's find out the data points with these dates and fix them. I put in the date that has an error. The data point 1236 has an error. When we do the same thing for the second date, we get the data point as 737. We find out the data points for the other 2 dates. To fix the dates, we put in the actual date for each error. The actual IPO date for EM is 8/12/15, so we'll correct it, and the others based upon what a bit of research shows us as their true offering dates. These are the true dates, and when we run it, it's done. Running the function again will correctly add the 1-week change for all offerings. Now let's add the S&P 500 percentage change from the close the previous day of the IPO to the next day's opening of the IPO. So you need to run this code. It is a function getClose to open change. This is today's open and yesterday's close that we are using. Then we need to calculate the close to open percentage. This will generate close to open change percentage and also week change. Now let's tidy up the underwriter data. This is going to take some work. We'll perform a number of steps. First, we'll add a column for the lead underwriter or manager. Next, we'll standardize the data. Finally, we'll add a column representing the total count of underwriters involved. So, first we pass out the lead manager by splitting the data and removing white space. Next, printing out the different lead managers shows just how much cleanup is going to be required to standardize the bank's names. The code gives us the names of all the lead managers. There are 2 ways to do the cleanup if you're following along. The first way, and undoubtedly the easiest of the 2, is to trust that we have done the work for you and simply copy and paste the code provided in the code bundle. The other is to perform a lot of iterative partial string matching and correcting by yourself. The first option is strongly recommended. You have to copy the code from the file and paste it here. We are correcting each and every lead manager's name. After this process is complete, you can run the previous code again to see the updated list. This is the updated list. As we can see, the list is tidy now. With this completed, we'll add our count of underwriters. Next, we'll add a couple of date features. We'll add the day of the week and the month. This is the weekday and the month we are adding. So, in the output, you can see an added column of underwriters, weekdays and months. If all goes as expected, our data frame should look like this. We'll now add a couple of final features that relate to the change between the offer price and the opening and closing prices. We are calculating open to close percentage. That should do it for our features now. Let's print the IPOS. You can see the new features added here. We can always add more if we come across useful data that we think would improve the model, but this should get us started. However, before we start feeding these features to the model, we need to consider which features to select. We have to be extremely careful not to leak information when adding features. This is a common mistake that happens when information is provided to the model from data that would not be available at the time. For example, adding the closing price to our model would completely invalidate the results. By doing this, we would be essentially giving the model the answer it is trying to predict. Usually, leakage mistakes are more subtle than this, but they are a concern nonetheless. We'll add features such as month, day of the week, lead manager, offer to gap percentage, offering price, etc. With all of our model's features completed, we'll next prepare them for use by our model. We're going to use the Patsy library for this. Patsy can be pip installed if needed. Patsy takes data in its raw form and transforms it into a matrix that is appropriate for the building of statistical models. The output is here. We can see that Patsy has reconfigured our categorical data into multiple columns while keeping our continuous data in a single column. This is called dummy coding. In this format, each month except one will get its own column. The same is true for each broker. For example, if the particular IPO instance, row, was in May, then May will have 1 in the May column, while all the other month columns are for this row. There are always n-1 feature columns for each categorical feature. The one that is excluded becomes the baseline that the others are compared against. Finally, Patsy also adds an intercept column. This is a column of ones that is needed for regression models to function properly. With this completed, we'll move on to the modeling phase. In this video, we learned how to do feature engineering. Splendid! In the next video, we will look at binary classification. This is the third video of the section, binary classification. Previously, we performed feature engineering. In this video, we will perform binary classification using logistic regression. We will evaluate our model based on the classification score and also predict number of buys, wins, and losses. Instead of attempting to predict exactly what the total first-day return will be, we are going to attempt to predict if the IPO will be one we should buy for a trade or not. It is here that we should point out that this is not investment advice, and this is for illustrative purposes only. Please don't run out and start day trading IPOs with this model willy-nilly. It will end badly. Now, to predict a binary outcome, that is a 1 or 0, yes or no, we will start with a model called logistic regression. A logistic regression utilizes a logistic function. This is ideal as it has several mathematical properties that make it easy to work with. Due to the logistic function's form, it is particularly suited to providing probability estimates, and from these estimates, binary responses. Anything greater than 0.5 is classified as 1, and everything below 0.5 is classified as 0. These ones and zeros can correspond to anything we would like to classify. But in this application, it will determine if we buy the offering 1 or do not 0. Let's go ahead and apply this model to our data. We're going to split our data in a somewhat unusual way. The standard practice in machine learning models is to randomize which instances are fed to the model as training data and which are used as test data. However, because this data is time-based, we're going to use everything but the current year for training. We will then test on the 2015 year-to-date data. 2188 is the first index of the 2015 data. With this code, we split our data into training and test sets. Note that we also have arbitrarily set a dollar threshold for the positive outcome. This is intended to align with our strategy of targeting the long-tail winners rather than just any positive close. We will now fit the model using linear model.logistic regression function. You will get the fitted model details. We can now evaluate the model on our holdout 2015 data. You get the score here. From this, we can see about 74% of our predictions were accurate. This is certainly looking better than our baseline rate for 2015, but this can also be misleading, as the actual percentage of IPOs that gained more than $1 is very low. This means guessing 0 for all would give us about the same result. But let's compare the two. First, our baseline is as follows. The statistics of our data is shown. Next, we get our predicted results. We'll set up a data frame with our results first, then output them. You can see in the output that 2188 is the first index of the 2015 data. It will calculate the actual and predicted values. We get the stats for this now. So the total went from 254 buys to 39. Our mean went from $0.14 to $2.18. Let's look at a plot of our returns. You can see the returns plot here. From this, it looks like we got the big winner of the year along with a couple of other minor wins and losses. This isn't a lot to go on as far as a test of our model. We could have just been very lucky to catch this win. We need to assess the robustness of our model. We can do this in several ways, but let's do just two things. We'll first drop our threshold from $1 to $0.25 to see how the model holds up. So we run the same code, but change the threshold this time. Let's have a look at the score. It's 0.5693. That is, 57% is the accuracy of our model. Now we'll examine our results. The output is here. Looking at the results, our accuracy dropped, as did our mean. However, our count went from 39 to 74, and we're still far above the baseline approach. Let's do one more test. Let's now remove 2014 from our training data and include it in our test. The 2014 data starts from 1900. Our accuracy is now almost 60%, so our accuracy went up. Once again, we'll examine the results. Here are all the values needed. With the 2014 included in our test data, you can see that our mean dropped, but the model continues to appear better than the naive approach of investing in every IPO as seen in this table. The count has increased from 74 to 84. Let's now move on to examine which features were most important in our model. In this video, we performed binary classification successfully. Awesome! In the next video, we will understand feature importance. Hi, welcome to the last video of this section, feature importance. In the previous video, we performed binary classification. In this video, we are going to understand feature importance. We will look at different features and their corresponding importance, which affects the final returns. Which features increase the probability that an offering will be successful? There is unfortunately no simple answer to this. However, we'll take a look at the two ways of assessing this. Because we built our model using a logistic regression, one thing we can examine is the coefficient for each parameter. Remember that the logistic function takes this form, ln of p by 1 minus p is equal to b0 plus b1 of x. Here p represents the probability of our positive outcome. b0 is our intercept and b1 is the coefficient for our feature. Once we fit our model, these coefficients can be examined. Let's retrieve them now. The output shows the coefficients and the corresponding features. For categorical features, a positive sign on the feature coefficient tells us that when present, this feature increases the probability of a positive outcome versus the baseline. For continuous features, a positive sign tells us that an increase in the value of this feature corresponds to an increase in the probability of positive outcome. The size of the coefficient tells us the magnitude of the increase in probability. Let's examine this by looking at the days of the week. We get the days of the week. From this we see that Friday is missing. This means that Friday is the baseline against which all other treatments are compared. We also see that only Thursday has increased odds of having a successful IPO based on our model. It is important to note that the coefficient does not represent the actual increase in odds over the baseline. To get this value, we must take the exponential of it. For Thursday, the increase in odds over Friday is 1.0077. This means that holding all else constant, the odds that Thursday will have a successful IPO are 0.7% greater than Friday. We can also see that Monday is the worst day of the week for IPOs, about a 46.7% decrease in the odds of a successful IPO. Coming back to feature importance, you most likely think at this point that you can take the features with the largest positive coefficients, throw them into a model, and you'll have everything that you need to dominate the new issue market. Not so fast. Let's look at top 2 features based on the size of their positive coefficient. The top 2 features are Keegan and Tubin. Our top 2 features represent a sum total of IPOs. This is why it is difficult to extract this information from logistic regression models, especially ones of this complexity. All is not lost, however. We can utilize another model known as a random forest classifier to get our importance measures. This video won't go into depth about how this model works, but it should give similar results to the logistic regression model, and as a bonus, it will provide a very nice summary of which features have the highest influence on a positive outcome. Using the same training and test data as earlier, we'll fit the random forest classifier. This is the code for that. The fitted model generates this output. The output from this gives us a ranked list of feature importance, along with error bars for each. Looking at the list, these rankings would seem to make sense, with gap opening percentage and dollar change from opening leading the pack. In this video, we have studied important features and worked with them. Great! We've covered a lot of ground in this section, but we've only just cracked the surface of how to build this type of model. Hopefully, you've gained a better understanding of the modeling process from cleaning the data to engineering the features to testing. Hopefully, you'll use this information to extend the model on your own and improve upon it. In the next section, we'll turn our attention to a very different domain as we move from numerical data to text-based data. That is, we will create a custom news feed. Hello, this is a new section of the course. Create a custom news feed. In this section, we will create a supervised training set with Pocket App. We will then retrieve stories using Pocket API. We will then use embed.ly API to extract story bodies. We will then look at natural language processing basics, support vector machines. We will also perform IFTTT integration with RSS feeds and Google Sheets. Finally, we will set up a daily personal newsletter. So let's start with the first video of the section, creating a supervised training set with the Pocket app. In this video, we will look at how to install and set up Pocket API. We will also retrieve articles and arrange them. Before we can create a model of our taste in news articles, we need training data. This training data will be fed into our model in order to teach it to discriminate between the articles that we'd be interested in and the ones we would not. To build this corpus, we will need to annotate a large number of articles that correspond to these interests. For each article, we'll label it either Y or N, that is yes or no. This will indicate whether the article is one that we would want to have sent to us in our daily digest or not. To simplify this process, we will use the Pocket app. Pocket is an application that allows you to save stories to read later. You simply install the browser extension and then click on the Pocket icon in your browser's toolbar when you wish to save a story. The article is saved to your personal repository. One of the great features of Pocket for our purposes is its ability to save the article with a tag of your choosing. We'll use this feature to mark interesting articles as Y and non-interesting articles as N. Let's start with installing the Pocket Chrome extension. We use Google Chrome here, but other browsers should work similarly. For Chrome, go into Google App Store and look for the Extensions section and search for Pocket. You can see the Pocket extension here. Click on the blue Add to Chrome button. If you already have an account, log in, and if you do not have an account, go ahead and sign up. It's free. Once this is complete, you should see the Pocket icon in the upper right-hand corner of your browser. It will be grayed out, but once there is an article you wish to save, you can click on it. It will turn red once the article has been saved. The grayed out icon can be seen in the upper right-hand corner. When the icon is clicked, it turns red to indicate the article has been saved. Now comes the fun part. Begin saving articles all that you come across. Tag the interesting ones with Y and the non-interesting ones with N. This is going to take some work. Your end results will only be as good as your training set, so you're going to need to do this for hundreds of articles. If you forget to tag an article when you save it, you can always go to the site getpocket.com to tag it there. So just click on Edit Tags and tag it as n.tag, the interesting articles as Y. You can just click on Save here and it will be added to your list. I am trying to save as many articles as possible to get a better output. Now that you've diligently saved your articles to Pocket, the next step is to retrieve them. To accomplish this, we'll use the Pocket API. You can sign up for an account at this site. Click on Create New App on the upper left-hand side and fill in the details to get your API key. So I will fill in the details here. Make sure to click all of the permissions so that you can add, change, and retrieve articles. You also need to select the platform, so I would like to select for extension. Click on Create Application. Once you have filled this in and submitted it, you will receive your consumer key. Here is the key. Once this is set, you are ready to move on to the next step, which is to set up the authorizations. We'll do this now. It requires that you input your customer key and a redirect URL. The redirect URL can be anything. Here I have used my Twitter account. Copy the consumer key and we will use this to set up the authorization. First, we need to import some libraries, that is pandas, request JSON, and set the maximum column width as 200. Then we create the authorization parameters. This consumer key will be copied here. And I'm giving the redirect URL as my Twitter account. So we need to pass the authorization request site to request library and authorization parameters as data. The output will have the code that you'll need for the next step. Copy the code. Go to the browser, paste the URL. When you click Enter, you get this page. If you change the redirect URL to one of your own, make sure to URL encode it. There are a number of resources for this. One option is to use the Python library urllib. Another is to use a free online source. At this point, you should be presented with an authorization screen. Click on Authorize. When you do that, you are redirected to your Twitter account. Now we will again go back to our IPython file. This is the code. Replace the consumer key with your own, and you'll need to copy this code and place it here. You have to do this for each step. This generates an access token. First, we retrieve the stories tagged N. You remember we had tagged stories as Y and N? So let's start with that. This is the code. Here again you have to use your consumer key and this access token here in place of some super long code. OK, we have missed a 4 here. Please do check properly. When we run it again, we will get this output. Note that we have a long JSON string on all the articles that we tagged N. There are several keys in this, but we are really only interested in the URL at this point. We'll go ahead and create a list of all the URLs. First, we load the JSON files, then create a list out of it and append all the URLs in the noURLs variable. These are the sites which we tagged as N. This list contains all of the URLs of stories that we aren't interested in. Now, let's put this in a dataframe object and tag it. We will pass the noURLs as data and name the column as URLs. The output is the list of URLs along with the wanted status, that is, no. Now we're all set with the unwanted stories. Let's do the same thing with the stories we are interested in. First, we need to get all stories tagged as yes. We will copy the previous code and change no to yes. The consumer key and access token will remain the same. When we run it, you will get a list of stories you are interested in. We need to sort this out, so we run this code to get the resolved URL. Let's print the URLs. These are the sites we are interested in. Let's create a data frame like we did previously. You can see a list is created here. Now that we have both types of stories for our training data, let's join them together into a single data frame. You are using the concat function to join the yes URL and no URL. A single data frame is created for yes and no URL. Now that we're set with all our URLs and their corresponding tags in a single frame, we'll move on to downloading the HTML for each article. We'll use another free service for this called embed.ly. So, we got the supervised training set with Pocket App here. In the next video, we will use embed.ly API to download story bodies. This is the second video of the section, using the embed.ly API to download story bodies. In this video, we will set up the embed.ly first. Then, we will get story bodies using the API. We have all the URLs for our stories, but unfortunately this isn't enough to train on. We'll need the full article body. This could become an enormous challenge if we needed to build our own scraper for dozens of sites. We would need to write code to target the article body while carefully avoiding all the other site gunk that surrounds it. Fortunately, there are a number of free services that will do this for us. We're going to be using embed.ly to do this, but there are a number of other services that you also could use. The first step is to sign up for embed.ly API access. You can do this at this site. This is a straightforward process. Once you confirm your registration, you will receive an API key. This is really all you'll need. You just use this key in your HTTP request. Let's do this now. You will get 3 tabs here, so you can choose any one. I am connected to Twitter. If you are a software developer, you can go through this. Here, click on the second option and give the link forgetpocket.com. You can create an account here. And move further. You will get this screen. Enter the name of your project and click on Create. When you do that, you will get this screen where you will get a key. Copy the key and go to IPython file. Run this code where API key is supposed to be replaced, and the URL. First, we import the URL lib library. Then, we are creating a function, getHTML, in which we are passing the URL lib library and amking request to URL of that site using the API key, which we have generated, loading the JSON file, and we are mapping the content. It will take a little time. With that, we have the HTML of each story. You will see the URL on one side and the HTML content on the right. We need to feed plain text to our model rather than HTML, so we will use a parser to strip out the markup tags. So this is the code you need to run for that. Here we are importing the beautiful SOAP library, and we are creating the getText function. Here we get the actual text of our story. So in this video, we downloaded story bodies using embed.ly API. In the next video, we will look at natural language processing basics. Hi, welcome to the third video of the section, Natural Language Processing Basics. Previously, we downloaded story bodies using embed.ly API. In this video, we will learn about natural language processing. We look at how text is converted into numerical data and features are extracted. If a machine learning model only operates on numerical data, how can we transform our text into a numerical representation? This is the focus of natural language processing, or NLP. We will need to get a brief overview of the principles of NLP before we can work our data. And rather than using the data we have already collected from Pocket, we'll work with a minimal example to keep it simple enough to illustrate the principles. Once those are clear, we can then apply them to our newsfeed corpus. We'll begin with a small corpus of 3 sentences. The new kitten played with the other kittens. She ate lunch. She loved her kitten. We'll first convert our corpus into a bag of words, BOW representation. We'll skip pre-processing for now. Converting our corpus into a bag of words representation involves taking each word and its count to create a term document matrix. In a term document matrix, each unique word is assigned to a column, and each document is assigned to a row. At the intersection of the two is the count. The table shows that. Note that for these 3 short sentences, we already have 12 features. As you can imagine, if we were dealing with true documents, such as news articles or even books, the number of features would explode into the hundreds of thousands. To mitigate this, we can take a number of steps to remove features that add little to no informational value to our analysis. The first step that we can take is to remove stop words. These are words that are so common that they typically tell you nothing about the content of the document. Common examples of English stop words are the, is, at, which, and on. We'll remove these and recompute our term document matrix. The table is seen here. As you can see, the number of features was reduced from 12 to 7. This is great, but we can take it even further. We can perform stemming or lemmatization. We can consolidate this into just kitten. Our new matrix consolidated kittens and kitten, but something else happened as well. We lost the suffixes to played and loved, but ate was transformed to eat. Why? This is what lemmatization does. If you remember your grade school grammar classes, you've gone from the inflectional form to the base form of the word. Now, if lemmatization is the transformation to the base form of a word, what is stemming? Stemming has the same goal, but it uses a less sophisticated approach. This approach can sometimes produce pseudo-words rather than the actual base form. For example, in lemmatization, if you were to reduce the word ponies, you would get pony. With stemming, you would get pony. Now let's go further to apply another transformation to our matrix. So far, we used a simple count of each word, but we can apply an algorithm that will act like a filter on our data to enhance the words that are unique to each document. This algorithm is called Term Frequency Inverse Document Frequency, or TF-IDF. We calculate this TF-IDF ratio for each term in our matrix. Let's calculate it for a couple of examples. For the word new in document 1, the term frequency is just the count, which is 1. The inverse document frequency is calculated as the log of the number of documents in the corpus over the number of documents the term appears in. For new, this is log 3 divided by 1, or 0.4471. So for the complete TF-IDF value, we have TF into IDF. Or here, it is 1 times 0.4471, or just 0.4471. For the word kitten in document 1, the TF-IDF is 2 into log 3 over 2, or 0.3522. Completing this for the remainder of terms and documents, we have this table. Why do all of this? To obtain a high TF-IDF value, a term would need to have a high number of occurrences in a low number of documents. In this way, documents can be said to be represented by terms with high TF-IDF values. With this framework, we'll now convert our training set into a TF-IDF matrix. For this, we run this program. With these 3 lines, we have converted all our documents into a TF-IDF vector. A couple of points to note. We passed in a number of parameters: n-gram, range, stop, words, and min-df. Let's discuss each of these. First, n-gram range is how the document is tokenized. In our prior examples, we used each word as a token, but here we are using every 1 to 3 word sequence as tokens. Let's take our second sentence. She ate lunch. We'll ignore stop words for the moment. The n-grams for this sentence would be she ate lunch, ate lunch, and lunch. Next, we have stop words. We pass in English for this to remove all the English stop words. As discussed previously, this removes all terms that lack informational content. Finally, we have min-df. This removes all words from consideration that don't appear in at least 3 documents. Adding this removes very rare terms and cuts down on the size of our matrix. Print the TV value. The output shows that 10,557 elements are compressed. Now that our article corpus is in a workable numerical format, we'll move on to feeding it to our classifier. In this video, we have learnt natural language processing successfully. Amazing! In the next video, we will work with support vector machines. This is the 4th video of this section, Support Vector Machines. Previously, we understood natural language processing basics. In this video, we will first try to look at linear classification of data. We will also look at soft margin SVM and kernel trick. We're going to be utilizing a new classifier in this video, the linear support vector machine. A support vector machine is an algorithm that attempts to linearly separate data points into classes using a maximum margin hyperplane. This is a mouthful, so let's look at what this really means. Suppose we have 2 classes of data and we want to separate them with a line. We'll just deal with 2 features or dimensions here. What is the most effective way to place this line? In this figure, line H1 does not effectively discriminate between 2 classes, so we can eliminate this one. Line H2 is able to discriminate between them cleanly, but H3 is the maximum margin line. This means that the line is centered between the 2 nearest points of each class, which are known as the support vectors. These can be seen as a dotted line in this figure. But what if the data isn't able to be separated into classes so neatly? What if there is overlap between the points? In this situation, there are still options. One is to use what's called a soft margin SVM. This formulation still maximizes the margin, but with the trade-off being a penalty for points that falls on the wrong side of the margin. The other option is to use what's called the kernel trick. This method transforms the data into a higher dimensional space, where the data can be linearly separated. This is the site where you can find the kernel trick documentation. Here we have 2 classes that cannot be separated with a single linear plane. But the implementation of a kernel maps our previous image into a higher dimension, as seen below. This allows the data to be linearly separated. We have taken a 1-dimensional feature space and mapped it onto a 2-dimensional feature space. The mapping simply takes each x value and maps it to x2. This transformation allows us to add a linear separating plane. Let's feed our TF-IDF matrix into SVM model. The TV parameter is our matrix, and the df Wanted method is our list of labels. Remember, this is either Y or N, representing if we are interested in the article or not. Once this runs, our model is trained. One thing we aren't doing in this chapter is formally evaluating our model. You should almost always have a holdout set to evaluate your model against, but because we are going to be continuously updating our model and evaluating it daily, we'll skip this step for now. Just remember, this is generally a terrible idea. Let's now move on to setting up our daily feed of news items. So in this video, we performed linear classification with SVM successfully. Awesome! In the next video, we will integrate our feeds, Google Sheets, and email. Hi, welcome to the 5th video of this section, IFTTT integration with feeds, Google Sheets, and email. In the previous video, we learnt about support vector machines. In this video, we will integrate Google Sheets, feeds, and email using IFTTT. We used Pocket to build our training set, but now we need a streaming feed of articles to run our model against. To set this up, we'll use IFTTT once again, as well as Google Sheets and a Python library that will allow us to work with Google Sheets. Setting up news feeds and Google Sheets through IFTTT. Hopefully, you have an IFTTT account set up at this point, but if not, go ahead and set this up now. More details can be found in the section Build an app to find cheap airfares. Once this is done, you'll need to set up integration with feeds and with Google Sheets. I will go to the site ifttt.com. First, click on Search. Search for feeds. Then click on Feed and click on Connect. Once this is done, go to Search Engine again and search for Google Drive. Click on Google Drive and click on Connect. Click on this. It should take you to a page where you select the Google account that you want to connect to. Choose the account and then click on Allow to enable IFTTT to access your Google Drive account. Once this is done, you should see something like this. Now with our channels connected, we can set up our feed. Click on My Applet and then on New Applet. That will bring you here. Click on this. Search for feed. You can see 2 tabs here, New Feed Item and New Feed Item Matches. Click on the New Feed Item. This should bring you here. We will add this URL here. Then click on Create Trigger. Once this is done, you'll be brought back to add to that action. Click on that. Search for Google Drive, and then click on its icon. Once this is done, you'll find yourself here. We want our news items to flow into a Google Drive spreadsheet, so click on Add Row to Spreadsheet. You'll then have an opportunity to customize the spreadsheet. You can save the name as New Stories, and you can just specify the Drive folder path as this. I gave this spreadsheet the name News Stories and placed it in a Google Drive folder called IFTTT. Click on Create Action to finish this, and soon you'll start seeing news items flow into your Google Drive spreadsheet. Note that it will only add new items as they come in, not items that existed at the time you created the sheet. Click on Finish. I recommend adding a number of feeds. You will need to create individual recipes for each. It is best if you add feeds for the sites that are in your training set, for example, the ones you saved with Pocket. Give the stories a day or two to build up in the sheet. They should look something like this. Fortunately, the full article HTML body is included. This means we won't have to use embed.ly to download it for each article. We will still need to download the articles from Google Sheets and then process the text to strip out the HTML tags. But this can all be done rather easily. To pull down the articles, we'll use a Python library called gspread. So open Command and pip install it. Once that's done, you'll need to follow the directions to set up OAuth 2. This can be found on this site. You will end up downloading a JSON credentials file. Once you have this file, you can find the email address in it with the client email and the client email key. You then need to share the new stories spreadsheet that you are sending the stories to with that email. So let's go to Google Chrome. Go to your sheet. Just click on the blue Share button in the upper right-hand corner of the sheet and paste the client email in here. You will end up receiving a failed to send message in your Gmail account, but this is expected. Make sure to swap in your path to the file and the name of the file. So let's go back to our editor. Here we are importing the gspread and .json file and service account credentials. You need to give the scope as your Google spreadsheet link and give the path of your .json file here. Lastly, we authorize the credentials. Now, if everything went well, it should run without errors. Next, you can download the stories. Let's run this. It may take some time. You can see the output here with the title URL and HTML tags. With this, we downloaded all of the articles from our feed and placed them into a data frame object. We now need to strip out the HTML tags. We can use the function that we used earlier to retrieve the text. We'll then transform it using our TF-IDF vectorizer. This is the output. Here we see that our vectorization was successful. Let's now pass this into our model to get back the results. We are passing the tset matrix to our model. Let's print our results. You can see that we have results for each story. Let's join this with the stories themselves so that we can evaluate the results. We use the pd.merge function for it, so you can see that all the wanted and tagged stories are there, here with their content. Definitely nailed these two as per our interest. At this point, we can improve the model by going through the results and correcting errors. You'll need to do this for yourself, but here is how I made changes to my own. These are the index number of the stories which I want to change to no, and the ones I want to change to yes. Once that is done, we need to run a for loop to change the indexes. So here is what we get. You can check the index of 534. It is changed to yes. This may look like a lot of changes, but for over 900 articles evaluated, I had to change very few. By making these corrections, we can now feed this back into our model to improve it even more. Let's add these results to our early training data and then rebuild the model. You can see the stories tagged as Y and N. Now we rebuild the model. We have now retrained our model with all available data. You may want to do this a number of times as you get more results over the days and weeks. The more that you add, the better your results will be. We'll assume you have a well-trained model at this point and are ready to begin using it. Now let's see how we can deploy this to set up a personalized news feed. So in this video, we have integrated Google Sheets, feeds, and email. Splendid! In the next video, we will set up a personalized daily newsletter. Hi, this is the last video of the section, setting up your daily personal newsletter. In the previous video, we integrated Google Sheets, feeds, and email using IFTTT. In this video, we will set up custom feed to get daily newsletters in our email account. In order to set up a personal email with news stories, we're going to utilize IFTTT again. As we did before, we'll use the Maker channel to send a post request. So we search for Maker, click on it, then click on Connect. Instructions can be found in the section Build an app to find cheap airfares. You should also set up the Gmail channel in the same way. Directly use your email ID. Once that is complete, we'll add a recipe to combine the two. First, click on My Applets, then create an applet from the IFTTT homepage. Then search for the Maker channel. Select this, then select Receive a web request. Then give the request a name. I'm using News Event. Finish by clicking on Create Trigger. Next, click on that to set up the email piece. Search for Gmail and click on the icon. Once you have clicked on Gmail, click on Send an email. From here, you can customize your email message. Input your email address, a subject line, and finally include Value 1 in the email body. We will pass our story title and link into this with our post request. Click on Create Action and then Finish to finalize this. Now we're ready to generate the scripts that will run on a schedule, automatically sending us articles of interest. We're going to create a separate script for this, but one last thing that we need to do in our code is serialize our vectorizer and our model. This can be done by this code. We will import pickle, and we need to dump these two model.pickle and vectorization file. With this, we have saved everything that we need from our model. In our new script, we will read these in order to generate our new predictions. We're going to use the same scheduling library to run the code that we used in a previous section, build an app to find cheap airfares. Putting it all together, we have the following script. We are loading the model here with the load function from the same location where we have saved it. Then we are authorizing the credentials. Then we are getting HTML text and running the model. What this script will do is run every 60 minutes, pull down the news stories from Google Sheets, run the stories through the model, generate an email by sending a post request to IFTTT for the stories that are predicted to be of interest. And then finally, it will clear out the stories in the spreadsheet so that only new stories get sent in the next email. Congratulations! You now have your own personalized news feed. Keep this running. It will give you emails like this: subject ads, new digest. It will add stories from the Google Sheet. Initially, you may see a failed message, but as your news stories are fetched and fed into Google Sheets, they would be sent to your mentioned email ID with the subject as New Digest, as shown in the video. We created a custom news feed successfully. Awesome! In this section, we learned how to work with test data when training machine learning models. We also learned the basics of NLP and support vector machines. Finally, we integrated our feeds and email and set up our personalized newsletter. In the next section, we'll take a look at forecasting the stock market with machine learning. Hi, and welcome to the fourth section, Forecast the Stock Market with Machine Learning. In this section, we'll spend some time discussing how to build and test a trading strategy. We'll spend even more time, however, on how not to do this. There are countless pitfalls to avoid when trying to devise your own system. It is quite nearly an impossible task. We will also evaluate our model's performance. Now we move on to the first video of this section that deals with what does research tell us about the stock market? In this video, we are going to look at the research of the stock market and what it reveals. Just like living organisms, markets evolve, and what works one day quickly fails to work the next. For example, occasionally a paper will be published that alerts the financial world to the existence of a phenomenon that is based upon some profitable anomaly. Frequently, this phenomenon is the downstream effect of some outside imposed real-world constraint. Take, for example, year-end tax loss sales. Due to the nature of tax laws, it makes sense for traders to sell their losses at the end of the year. This causes downward price pressure to appear on the losing stocks towards year-end that causes the stocks to be discounted beyond their fair market value. This also means that in January, the downward pressure is gone and in its place is upward pressure as new money is put to work in these now undervalued assets. Once this phenomenon has been broadcast, however, it only makes sense for traders to attempt to get ahead of it and begin buying those stocks in late December and selling to other traders in January. These new traders seeking to gain an early edge now dilute the effect by entering the market. They are relieving the year-end selling pressure and decreasing the January buying pressure. The effect is essentially arbitraged away right along with the profitability. What once worked no longer works, and the traders begin to abandon the strategy and move on to the next new thing. To stay in the same place, traders must quickly adapt. Perhaps the most influential theory of the stock market over the last 50 years is the efficient market hypothesis. This theory was developed by Eugene Fama, and it states that markets are rational and all available information is adequately reflected in stock prices. As such, it is impossible for an investor to consistently beat the market on a risk-adjusted basis. The efficient market hypothesis is often discussed as having three forms: a weak form, a semi-strong form, and a strong form. In the weak form, the market is efficient in the sense that one cannot use past information from prices to predict future prices. Information is reflected in stocks relatively quickly. Also, while technical analysis would be ineffective, in some scenarios, a fundamental analysis could be effective. In the semi-strong form, prices immediately reflect all the relevant new public information in an unbiased manner. Here, neither technical nor fundamental analysis would be effective. Finally, in the strong form, stock prices reflect all public and private information. Based on these theories, there isn't a lot of hope of making money by exploiting patterns in the market. Fortunately, while the market operates in a largely efficient manner on the whole, distinct pockets of inefficiency have been uncovered. Most of these tend to be ephemeral, but some do persist. One of the most pervasive, even according to Fama, is the outperformance of momentum strategies. So what exactly is a momentum strategy? There are a number of variations on the theme, but the basic idea is that stocks are ranked from the highest to lowest according to their return over some prior period. The top performers are bought and held for some period of time, and then the process is repeated after some fixed holding period. A typical long-only momentum strategy may involve buying the top 25 performing stocks in the S&P 500 over the past year, holding them for a year, and then repeating the process. This may sound like an absurdly simple strategy, and it is. However, it has consistently returned results that defy expectation. Why? As you can imagine, a lot of research has examined this effect, and the hypothesis is that there is something inherently, systematically biased about how humans deal with new information. Research suggests that they underreact to news in the short term and then overreact to news in the long term. Will this effect be arbitraged away as more traders learn of it and pile in? There has been some evidence of this in recent years, but it remains unclear. Regardless, the effect was real and persisted far longer than can be currently accounted for by the efficient market hypothesis, so there is hope. With this slight glimmer of hope, let's now move on to seeing how we may go about finding our own anomalies. In this video, we have studied the stock market and analyzed it for the further task. Splendid! In the next video, we will see how to develop a trading strategy. This is the second video of the section, Developing a Trading Strategy. In the previous video, we did research about the stock market. In this video, we are going to understand the different statistics for a particular span of time. Then, we are going to extend our analysis and check the returns for that time, and check the profitability of our strategy. We'll begin our strategy development by focusing on the technical aspects. Let's take a look at the S&P 500 over the last several years. We'll use the functionality of pandas to import our data. This will give us access to several sources of stock data, including Yahoo and Google. First, we need to install the data reader package. This can be pip installed from the command line using pip install pandas data reader. You can see that it is already installed here. Then we'll go ahead and set our imports as follows. So we will use Jupyter to do that. Let's go to Jupyter. Then we create a new Python file and import some packages. Once it is done, you need to initiate the matplotlib and set the option as 200. Now we'll get our data for the SPY ETF. This instrument represents the stocks of the S&P 500. We'll pull data from the start of 2010 through the beginning of March 2016. So this is the code we need to implement for that. So here we are setting the start date as 1st of January 2010 and the stop date as 1st of March 2016. We will get the data from Yahoo, that is SPY data. You can see the output here. It contains columns for high price, low price, open price, close price, the volume, and the adjacent close for 2010 to 2016. We can now plot our data. We set only the closing price here. We will then plot the graph. You will see this graph. We can see the price chart of the daily closing price of the S&P 500 for the periods that we selected. Let's run a bit of analysis to see what the returns over this period could have been if we had invested in this ETF. We'll pull data for the first open first. This is the value of the first open, $11,237. Next, let's get the closing price on the final day of the period. This will result in this output. And finally, let's see the change over the full period. We have to subtract the first open from the last close. You can see it is around $8,573. So it appears that a purchase of 100 shares at the start of the period would have cost us approximately $11,237, and at the end of the period, that same 100 shares would have been valued at roughly $19,811. This transaction would have given us a gain of over 76% over the period. Not bad at all. Let's now take a look at the return over the same period for just the intraday gains. This assumes that we buy the stock at the open of each day and sell it at the close of the same day. To do that, this is the code. We need to subtract the open price from the close price. This will give us the change from the open to the close each day. Let's take a look at this. You can see the list of daily changes of each day starting from 2010 till March 2016. Let's now sum those changes over the period. The code generates the output 43.36 points. So as you can see, we have gone from a gain of over 85 points to one of just over 43 points. More than half the market's gains came from holding overnight during that period. The overnight returns were better than the intraday returns, but how about the volatility? Returns are always judged on a risk-adjusted basis, so let's take a look at how the overnight trades compared to the intraday trades on the basis of their standard deviation. We can use NumPy to calculate this for us, as follows. We have already imported the NumPy as NP, so this is the code to calculate the standard deviation for daily change. Oops, I haven't imported NumPy. So here I will do that and run the command again. Okay, now you can see the standard deviation. Now, let's get the standard deviation for overnight change. You can see the value here. So our overnight trading had lower volatility as compared to the intraday trading as well. However, not all volatility is created equal. Let's compare the mean change on downside days versus upside days for both strategies. First, let's look at the upside days. This is the code you need to run. You can see the output here. Now we'll look at the downside days, that is the mean of the overnight change. The value is minus 0.66. Again, we see that the average downside move is less for our overnight trading strategy versus our intraday trading strategy. So far, we looked at everything in terms of points, but let's now move to looking at returns. This will help put our gains and losses in a more realistic context. Continuing with our 3 strategies, we'll construct a pandas series for each scenario: daily returns, close to close change, intraday returns, open to close, and overnight returns, close to open. To do that, we enter this code. This is the daily return. This is the intraday return, and this is the overnight return. What we've done is use the pandas shift method to subtract each series from the prior day's series. For example, for the first series in the preceding code, we subtracted the close 1 day ago from the current closing price for each day. So this is the prior day's calculation. A new series is generated that contains 1 less data point due to the differencing. If you print out the new series, you can see this output. This is the change of daily returns. Similarly, we can print out the intraday return and overnight return. Let's now take a look at the statistics for all 3 strategies. We'll create a function that can take in each series of returns and will print out the summary results. We're going to get statistics for each of our winning, losing, and break-even trades, and something called the Sharpe ratio. I said earlier that the returns are judged on a risk-adjusted basis. This is exactly what the Sharpe ratio provides us. It is a method of comparing returns by accounting for the volatility of these returns. Here we use the Sharpe ratio with an adjustment to annualize the ratio. Let's create the function. This is the function that we have created, called getStats. Here we are calculating the wins, losses, mean, standard deviation, max, Sharpe ratio, count, etc. Let's now run each strategy to see the stats. We'll start with the buy and hold strategy, daily returns, and then move to the other 2. You just need to call the function and pass daily return to it. You can see the details of daily returns as output. Similarly, we will see for intraday returns, and we can do the same for overnight return. As you can see, the buy and hold strategy has the highest mean return as well as the highest standard deviation of the 3. You can see the mean values here. This also has the largest daily drawdown, loss. Also notice that even though the overnight-only strategy has nearly the same mean return as the intraday strategy, it has substantially less volatility. This in turn gives it a Sharpe ratio that is higher than the intraday strategy. At this point, we have a solid baseline to compare our future strategies. Now, I'm going to tell you about a strategy that blows all 3 of these strategies out of the water. Let's now extend our analysis. First, we'll pull data for the index starting from the year 2000. We are setting the start date as January 2000 and the stop date as March 2016. Let's have a look at our chart now. This is the chart. Here we see the price action for the SPY from the start of 2000 through March 1st, 2016. There has certainly been a lot of movement in that period, as the market has experienced both highly positive and highly negative regimes. Let's get our baseline for our new expanded period for our 3 based strategies. First, let's set up our variables for each of them as follows. This is the code for that. Now, let's see what the point totals are for each of them. First for close to close. Here is the input for that. Then open to close. The value is minus 36.91. Finally, close to open. Now let's look at the statistics for each of them. We have already defined the function getStats. We just need to pass the required argument. First, get the statistic for close to close or long day return. Next, we retrieve the intraday return statistics. The corresponding output is displayed. Lastly, we show the overnight return statistics. We can see that the difference between the three are even more pronounced over a longer period. If we only held this S&P ETF during the day over the past 16 years, we would have lost money. If we held the ETF only overnight, we would have improved our returns by more than 50%. Obviously, this presumes no trading costs and no taxes, along with perfect fills. But regardless, this is a remarkable finding. You can compare the mean loss and the Sharpe ratio to compare the statistics. In this video, we have developed a trading strategy successfully. Splendid! In the next video, we will be building a model with support vector regression and evaluating model performance. Hello, this is the third video of this section, building a model and evaluating its performance. In the last video, we learnt to develop a trading strategy. In this video, we are going to build a regression model for prediction and evaluate its performance. Now that we have a baseline to compare to, let's build our first regression model. We're going to start with a very basic model using only the stock's prior closing values to predict the next day's close. We're going to build this model using a support vector regression. With this, let's set up our model. The first step is to set up a data frame object that contains price history for each day. We're going to include the past 20 closes in our model. You need to use this code to get the data. This code gives us each day's closing price, along with the prior 20, all on the same line. This will form the basis of the X array that we will feed our model. However, before we're ready for this, there are a few additional steps. First, we'll reverse our columns so that time runs left to right. So we reverse the code. You can see that it starts from 20 now. Now let's import our support vector machine and set our training and test matrices and our target vectors for each. We had just a bit over 4,000 data points to work with and choose to use the last 1,000 for testing. Let's now fit our model and use it to test out of-sample data, as follows. This is the line of code you need to run. It will consume a little time to run. You can see the star mark. Now that we have our predictions, let's compare them to our actual data. The preceding code generates the following output. This is how our output will look. You can see that the next day close and predicted next day close are very close. Let's now look at the performance of our model. We're going to buy the next day's open if the close is predicted to be higher than the open. We'll then sell at the close that same day. We'll next add a few extra data points to our data frame object to calculate our results as follows. This is the line of code I'm going to add. Here we are calculating the CD that is current day close and next day open. Then we are merging the data and then creating the column and printing it. You can see the output here. So the columns contain next day close, predicted next day close, current day close, and next day open. Here we'll add this code to get our signal and our profit and loss for the signal. We are going to create some functions. When we run the code, we get an error. In Python, if the code is not properly indented, it gives an indentation error. So we change the indentation, and now the code will run properly. Next, we are going to create a getReturn function. So this is the getReturn function. Once it is done, we are again going to calculate the TF2. This is the output you will get, where it is showing the signal and the PNL. Let's now see whether we were able to successfully predict the next day's price using just the price history. We'll start by calculating the points gained. You can see the sum as 2000. Not looking too hot so far. But what about the period that we tested? We never evaluated it in isolation. How many points would our basic intraday strategy have generated during the last 1000 days? So we calculate that. So it looks as if our strategy has failed to even match the basic intraday buying strategy. Because the difference between the two is too much, let's get the full stats to compare the two. Finally, the basic intraday strategy for the period is as shown here. The corresponding output is here. Now the results of our model are as follows. And the corresponding output. This looks bad. What if we modified our trading strategy? What if we only took trades that were expected to be greater by a point or more instead of just being an amount greater than the open? Would this help? Let's try it out. We'll rerun our strategy with a modified signal. Let's run the code again with a slight change. Here, we are calculating the get signal and get return and TF2. You get the output table as follows. Now we will calculate the sum. This is the sum. Now the stats are as follows. It looks like we do have a contrarian indicator here. When our model predicts strong next day gains, the market significantly underperforms, at least for our test period. Would this hold true in most scenarios? Not likely. Markets tend to flip from regimes of mean reversion to regimes of trend persistence. Let's rerun our model for a different period to test it further. This is the same code that we have done earlier. We train for a dataset of 2000 and test data of 2000 to 1000. So we can see that our new model and testing period returned over 33 points. Let's compare this to the intraday strategy for this same time period. This results in the following output. So it appears that our contrarian model significantly outperformed during a new testing period as well. At this point, there are a number of extensions that we could make to this model. We haven't even touched on using technical indicators or fundamental data in our model. And we have limited our trades to 1 day. All of this could be tweaked and extended upon. However, at this point, I want to introduce another model that uses a completely different algorithm. This algorithm is called dynamic time warping. What it does is give you a metric that represents the similarity between two time series. We will look at it next. Hi, this is the last video of the section, Modeling with Dynamic Time Warping. In the previous video, we built a model and evaluated its performance. In this video, we will start by calculating the Euclidean distance between t-series and arrange them using comparison measures. We will then plot them and then create a function to evaluate trades. Finally, we will get the statistical results. To get started, we'll need to pip install the fastdtw library from the command line using pip install fastdtw. Let's do that. You can see the requirement is already satisfied. Once this is done, we'll import the additional libraries that we'll need, as follows. We import the Euclidean and fastdw libraries. Next, we'll create the function that will take in two series and return the distance between them. We are calculating the Euclidean distance here. Now, we'll split our 16 years of time series data into distinct 5-day periods. We'll pair together each period with one additional point. This will serve to create our X and Y data, like this. We are creating a time series array here. We can take a look at our first series to get an idea of what the data looks like. So, we have to print the t-series. The t-series 0 contains 5 elements. Now that we have each series, we can run them through our algorithm to get the distance metric for each series against every other series. For that, we will create a method. So this is the method we are creating. Then we run this. It takes time to run. Once we have this, we can place it into a data frame object. We'll drop series that have 0 distance as they represent the same series. We'll also sort by the date of the series and look only at the ones where the first series is chronologically before the second. For that, we compare the series and arrange it. Finally, we'll limit our trades to where the distance is less than 1 and the first series has a positive return. Here the distance is less than 1 and the return greater than 0. The output shows that the distance between A and B is 0.77, where a return is 1.36 and B return is minus 1.69. This is for all the points. Let's see what one of our top patterns looks like when plotted. We use plt.plot for that. You can see the plot here. Now we'll plot the second one. The output is here. Notice something. As we can see, the curves are nearly identical, which is exactly what we want. We're going to try and find all of the curves that have positive next day gains. Then, once we have a curve that is highly similar to one of these profitable curves, we'll buy it in anticipation of another gain. Let's now construct a function to evaluate our trades. We'll buy the similar curves unless they fail to return a positive result. If this happens, we'll eliminate them. We will create a function called getReturns. Here is the function. Now that we have all the returns from our trades stored in return list, let's evaluate the results using the getStats function. We are passing the return list to get the statistics. Here are the details. These results are by far the best that we've seen. The win-loss ratio and the mean are far above our other models. It appears that we may be onto something with this new model, especially compared to the others that we've seen. At this point, to further vet our model, we should explore its robustness by examining other time periods for our matches. Does extending beyond the 4 days improve the model? Should we always exclude the patterns that generate a loss? There are many additional questions we could explore at this point, but I'll leave it as an exercise for the viewer. If you do utilize these techniques, know that we have just scratched the surface and that far more testing is required over additional windows to appropriately test these models. In this section, we took a look at the stock market. We learned how to formulate a trading strategy using machine learning. We built the first strategy using a support vector regression and the second using dynamic time warping. There is no doubt that the material of this section could be a course in itself. Many of the most important components of a trading strategy we didn't even cover. These include portfolio construction, risk mitigation, and money management. These are fundamental to any real strategy, arguably more important than trade signals. Hopefully, this will serve as a jumping point for your own explorations. However, again, I caution you that beating the market is a nearly impossible game. It is one in which you are competing against the brightest minds in the world. If you decide to try, I wish you the best of luck. Just remember that I warned you if it doesn't turn out like you hoped. In the next section, we will examine how to build an image similarity engine. Hello, this is a new section of the course. Build an image similarity engine. In this section, we will first look at the basics of image recognition. We will then work with images and find similar images on comparison. Finally, we will build an image similarity engine. So let's start with the first video of this section, Machine Learning on Images. In this video, we will have an introduction to applications of machine learning, such as digit recognition and facial recognition. We will also talk about Google's and Facebook's image search and deep face technology, respectively. So far in our journey, we have worked exclusively with numbers and text. In this section, we'll jump into the world of images. While this might seem to require some next-level wizardry, I can assure you that transforming images into machine-readable format is just as simple as transforming text is. We'll start out simply with what is arguably the hello world of image-based machine learning, digit recognition. By the end of the section, however, we will have constructed an advanced image-based deep learning application. To what noble end will we build this highly advanced application? Why, finding our spirit animal, of course. We'll also spend a fair amount of time covering deep learning algorithms to understand why they are so important and why there is so much hype surrounding them. While the applications of machine learning for text and numerical data tend to be the most discussed, there are similarly a large number of applications for images. Many of these tend to be in the areas of cutting-edge research with profound implications. We are quite accustomed today to running a Google search to find some odd snippet of text from a news story that we read 3 weeks ago and having the first result be just what we wanted. Now, imagine if we could do the same thing for pictures, movies, and GIFs. For example, let's say you saw a GIF 6 months ago that is perfectly apropos for your current Slack conversation. But all you can remember is that it involved a llama and a man trying to feed him. Right now, you'd have a tough time locating it because most image searches involve hashtags and the text surrounding the image. Over the last few years, however, companies such as Google have made amazing progress in having machines label the contents of images. When this research is fully realized and out in the wild, it will radically transform how we search for images. In this blog post from Google Research, they describe their progress towards this goal and explain some of the technical challenges in accomplishing it. For example, the image here shows 2 pizzas on top of a stove. In order to label the image as such requires not just an understanding of each of the objects, but their relationship to one another. And even then, the label needs to match up with a natural-sounding phrase, one that would likely match a human's description, for example. Even though it is technically correct, a person would never label it an oven under a pizza next to a pizza, right? Another application for machine learning for images is facial recognition. You may have heard about Facebook's deep face technology. It was reported that this application was so advanced it could actually recognize a person even if the image was of the back of their head, and it did this with near perfect accuracy. While this may seem to have frightening implications for society at large, for Facebook, this is invaluable technology. Once a person has been tagged in a single photo, no additional tagging is needed. All future photos tagging takes place automatically. It should be noted how difficult a task this is. Changes to a person's hair, clothing, age, not to mention the varying photo angles and lighting in each photo, make this an extraordinarily challenging task, even for people. In fact, just as computers have begun to surpass people on games such as Go, they are also beginning to best us on these types of recognition tasks as well. This new level of machine mastery comes from a relatively new class of algorithms that fall under the umbrella term deep learning. But first we'll take a look at the basics of how to work with images. So yes, we got a brief idea about image recognition in this video. In the next video, we will get hands-on with images and work with them. Hi, welcome to the second video of the section, Working with Images. In the previous video, we learnt about machine learning on images. In this video, we will first convert our handwritten images into pixelated formats, and then convert them into numerical values in a matrix. When we first introduced natural language processing, we learned that we would need to perform some sort of transformation in order to represent the words numerically. We did this by creating a term document matrix. Now that we're dealing with pictures, we'll need to perform another sort of transformation to render the images in a numeric form. Let's take a look at an image of a few handwritten digits. These particular digits are taken from the MNIST database of handwritten digits. This database contains tens of thousands of digits like this, collected from the handwriting samples of US Census Bureau employees and high school students. Let's suppose now that we wanted to use machine learning to recognize these digits. How might we represent them numerically from the data that we have? One way might be to map each pixel in our image to a value in a numeric matrix of the same size. We could then represent some property of that pixel as a value in our matrix. In fact, this is exactly how it's done. Each digit image is scaled and centered to give a canvas size 28 by 28 or 64 by 64 pixels. And then the color intensity of each pixel is represented as a value between 0 and 1 in our matrix, where 1 is pure black and 0 is pure white. This procedure is known as grayscaling. With this simple method, we turn a real-world thing into a numerical representation that can be utilized in our machine learning algorithms. Now let's take a look at a sample of this. We'll load the MNIST database available within the scikit-learn. So let's create a Jupyter notebook. Here we are importing the dataset from the sklearn package. The code will transform the image into a matrix of numbers. The digit can be seen in pixelated form. In the code, we loaded the necessary packages, followed by the digits dataset, and finally, we displayed the first digit using matplotlib. This is a crude representation because it is scaled to 8 by 8 or 64 total pixels. The actual matrix representation can be seen by running our next command, digits.images. And here is our matrix. These particular digits are scaled between 0 and 16, but we can see how they relate to the color intensity in the image at the level of each pixel. If we were to apply this to our algorithm, we would need to flatten the 8 by 8 matrix into a single vector of length 64. We can do that by running this function. This will then become a row, our feature vector, in our training set. We can also see the associated label for our data with the command digits.target. So you can see it is labeled 0. We now have everything we need to feed this image data into our algorithms. So far, we have only discussed how we would work with black and white images, but not surprisingly, working with color is just as simple. Each pixel can be represented using 3 features, one for each RGB value. Alternatively, the mean of 3 RGB values could be used if retaining a single feature was preferred. Now that we have transformed our images into a representation we can work with, let's take a look at which algorithms we might want to use. So in this video, we transformed our image into matrix form. Great! In the next video, we will compare images and find similar images. Hi, welcome to the third video of the section, Finding Similar Images. In the previous video, we worked with images. In this video, we will compare images and find similar images using the cosine similarity algorithm. We will do the same thing using the chi-squared kernel algorithm. Typically, the MNIST database of digits is used in classification tasks, that is, given the handwritten digit, find its target label. We'll be using it in a different manner here. For a given image, we'll attempt to find the image in the set that is most similar to it. This is an unsupervised task, as opposed to a supervised task, since we won't be making use of the labels. We'll start with an algorithm that we introduced earlier in the book when we dealt with text-based features. That algorithm is cosine similarity. Recall that this algorithm computes a unit vector for each row of our X matrix. The dot product of each against every other is then taken, which gives us the cosine angle between each vector. The end result is that we have a single metric that tells us how close 2 images are. Let's take a look now. First, we'll import the libraries that we'll need. The libraries imported are pandas and cosine similarity. Then we'll compute the similarity between the first image, our 0, and all other images. We do that using the cosine similarity function. As we are inputting a 1D array, scikit-learn will require that we reshape the array in the latest versions. Finally, we'll put the results in a pandas data frame object and take a look at our results. Here is our output. We can see that the first row is a 1, which means perfect similarity. because this is our original image. Below this are all the other images sorted by order of similarity. Let's take a look now at image number 877. We'll display it using the function that we created earlier, that is displayImage. You can see here we had created the function. We have to just pass the image number. This is image 877. We can see that this image is also a 0, showing us that we are on the right track. Let's take a look at image number 0 side by side with image number 877. We can see that these two zeros are remarkably similar. I would wager that they were created by the same person, in fact. Now let's have a bit of fun with this. What might we expect is the opposite of a 0? Let's find out. You can see that the least similar image is number 1626. When we display that image, what do we get? Yes, 1. Shockingly, we just confirmed binary coding. The opposite of a 1, in fact, is a 0. Hurrah! Let's now take a look at another algorithm that we frequently used in image-based machine learning applications. It is called the chi-squared kernel, and just like cosine similarity, it will give us a scalar value that tells us the similarity of two vectors. This is the mathematical formula of chi-squared kernel, where x and y are the two vectors. Let's look at how the chi-squared kernel similarity compares to the cosine similarity that we ran earlier. In this code, we are importing the chi-squared kernel. This is the output that we get, the digit number and the similarity values. While the order is somewhat different from the results of cosine similarity, most of the same values are present in the top values listed. Let's take a look at the most similar image from the chi-squared kernel. That is 1167. You can see a 0. Again, this 0 is remarkably similar to our original image. Why choose one of these, cosine similarity versus chi-squared kernel, over the other? While you can use either and get similar results, as we've seen, cosine similarity has proven to be the preferred choice for natural language processing work, while chi-squared kernels are the go-to choice for image-based tasks. At this point, it makes sense to wonder how we can possibly get from tiny black and white boxes containing a single digit to figuring out if an image is of a pizza, or a monkey, or a motorcycle. There just doesn't seem to be enough information to discern this from what we've done so far. And in fact, this is absolutely true. Just as we would have a nearly impossible time discerning Moby Dick from Pride and Prejudice using only counts of letters, we need to add another layer of abstraction. With text, this means using words and combinations of words, and with visual information, analogously, we use clusters of pixels. These clusters of pixels form what is called a visual vocabulary, and this method is known as a bag of visual words. The terminology was chosen because in the same way the text bag of words disregards word order, bag of visual words ignores the spatial order of its visual vocabulary. At this point, to further illustrate the bag of visual words process, let's walk through the concept at a higher level. Since the origin of bag of visual words comes from texture recognition, we'll use an example. Here, we have 3 different textures. Each comprises a repeating series of textual units, called textrons. These form the basis of our visual vocabulary. Each sample can then be represented as a histogram over these features as shown here. As we can see, the analogy holds closely to that of a bag of words, where each document is a histogram over words. Now at this point, I should point out that this description is primarily conceptual. There is far more involved in the actual implementation of a bag of visual words. The full details are beyond the scope of the book, but some of the work includes selecting points of interest for use as visual vocabulary and transformations that normalize and make the features scale invariant. Once the pre-processing is done, just as in text processing, a similarity matrix is computed, and the data is fed into the algorithm for classification. Again, like text processing, this is typically an SVM, that is, Support Vector Machine. In this video, we have compared and obtained similarity between images successfully. Awesome! In the next video, we will build an image similarity engine. Hi, this is the last video of the section, Building an Image Similarity Engine. In the previous video, we found similar images. In this video, we will find our spirit animal by building an image similarity engine. We will load a picture to find its nearest matches and pick out the best match. So let's start. It will be a lot of fun. If you made it this far through the section, you're now in for a treat. We will harness the power of the greatest advances in artificial intelligence to do something truly important. We will find your spirit animal. Well, not exactly. We will use it to find the cat you most look like in the CIFAR 10 images dataset. The CIFAR 10 dataset is a set of images used as a standard in computer vision research. It includes tens of thousands of images in 10 classes. Things such as dogs and frogs and airplanes and automobiles. Most importantly for us, however, this includes cats. Now, one thing to understand about deep learning is that of all the algorithms that we discussed, it tends to be the most powerful, but also the least friendly for the home gamers. By this, I mean this tends to require more training time and more computational horsepower to run than other algorithms. In fact, this is one of the reasons neural architectures were not adopted sooner. Only with the advent of cheap GPUs or graphical processing units did it become a workable option for researchers. Due to this, we will take two big measures to reduce processing time for our models. The first measure is to utilize GraphLab Create. Create is a popular framework for large-scale machine learning. This provides a nice API that is a bit like the steroid-fed love child of pandas and scikit-learn. Typically, it is used as a paid service. It requires a license, but this is offered free of charge for academic use, which appears to include boot camps and massive open online courses, MOOCs, such as Coursera. Make sure to check the site for details. GraphLab installation is straightforward. Details can be found on this site. Essentially, it just requires filling in a form to get a license and then copying and pasting the pip command they provide. You can click here to register. Once you register on a site, you will get a product key. Then you can click on View Instructions and use the Install GraphLab Create code on CMD to install GraphLab. Note that you will have to use Python 2.7. Python 3 is not supported at this time. The next measure that we will use to speed along the processing time is to use something called transfer learning. The idea behind transfer learning is to harness the power of massive, highly trained, deep learning networks, which are targeted to a very specific task. We then lop off the final layers and use these networks in order to use the lower levels as our features for a task that they have not been trained on. Remember, the lower levels have much less specificity in terms of aggregate representation of the item. In the world of digit recognition, the lower levels may be about representing loopiness or straightness, while the higher levels would be more about zero or oneness. In the world of elephant recognition, they are more about hand fanniness or tree branchiness. In transfer learning, we can extract those lower-level features in order to apply them to new domains, ones that they weren't specifically trained on. A lot of information in this section draws on the Coursera course on Machine Learning Foundations available at coursera.org. I highly recommend it if you are interested in going deeper into this material. With that, let's begin our coding. Our spirit animal awaits. We will begin with our imports. You can see that we are importing GraphLab and activating canvas.show. Wow! This is the GraphLab canvas that we can use. Next, you need to set the target as IPYNB. Next, we'll load the set of images that we'll use from the CIFAR 10 dataset. I am providing the link from where the images are being downloaded. It is being stored in GL image. This takes a considerable amount of time. The result would be this dataset. You will notice several columns of identifying information, such as the ID and the label, but you will also notice the column labeled Deep Features. These are the features that were extracted from a large trained deep learning network. We'll explain how we can use them in a bit. For now, let's keep moving. We can take a look at the images with this line of code. This code will show images of 5 columns. The images are exceedingly small, unfortunately, but you can resize them to be a bit more visible. I am resizing the image here, so we get a larger image. Now that we have all the images we'll need for making comparisons loaded, we'll just need to load in our own image. I will load in one of my own sample images that should be appropriate to this task. However, naturally, you'll need to load your own in that spot. Here is my image. Next, we need to get that image into the frame that contains our previously trained images. However, to do this, we'll need to extract its features. Let's do this now. So you can see the height and width of the image. And now we'll extract the image's deep features. For that, we need a model. We will get the model from this site. Then I am using the extract feature function of the deep learning model and passing the image to it. In addition to the height and width, we also see the deep features now. At this point, we just need a few final touches to get our image on par with the comparison images. We see that the max ID in the frame is 49,970. We will give my picture a value of 50,000, just to be easy to remember if necessary. You can see that the label is me and ID is 50,000. Almost there. Now we'll just join everything together using these columns. Okay, now we have one big frame with all our images and their deep features represented as a vector. At this point, we can use a very simple model to find the most similar image. We'll use k-nearest neighbors model first to compare one random cat to the others in the set, just to get a feel for the success of our model. We are passing the deep features column as features and ID as label. They are saying to start the brute force nearest neighbors model training. Let's get our test kitten. You can see a tiny kitten here. Therefore, this adorable pixelated little monster is our test subject. Let's find his doppelgangers. You can see that it is showing the distance and rank. That means the highest match has the least distance and vice versa. Now finally, let's look at our kitty matches. For that, I need to show the images of the top 5 matches. You can see the 5 images here. There we have it. Every image is a cat, and I'd say they look like our target kitty. Let's run it once again on another kitten. We will use image 145. This is our target. And now for his matches. We run the same test as before. You can see the output here. Next, we will display the matches. Now, on to the moment we've all been waiting for. Let's reveal my animal twin. I will load my image first and resize it. Now we'll run a search for my nearest match using the KNN model. The output is here. Next, we need to find the nearest neighbor from the dataset. Then we find the exact match. You can see that this image is pretty similar to my image, isn't it? I'll take it. I'm thinking it's all about the hat. But I will definitely accept him as my spirit animal. So we found our spirit animal today. Exciting! And of course, built the image similarity engine. Let's summarize the section. In this section, we had a grand tour of the highlights of machine learning for computer vision applications. we discussed a number of techniques used in the field and how to create a working application using a number of these techniques. We also discussed the principles of deep learning and how it can be applied for both feature extraction and classification. Most importantly, however, you now have a scientifically sound methodology for finding your spirit animal. In the next section, we'll take a look at how to create a chatbot application. Hi, and welcome to a new section, Build a Chatbot. In this section, we are going to learn how to construct a chatbot from scratch. Along the way, we'll learn more about the design and its future prospects. Now we move on to the first video of this section that deals with the design of chatbots. In this video, we are first going to see how a chatbot behaves and then look at the parameters involved in designing a chatbot. The original ELIZA application was 200-odd lines of code. The Python NLTK implementation is similarly short. An excerpt can be seen at the following link from NLTK's website. You can see the code here. Let's go to the IPython book. First, you need to import print function. Once that is done, you can form the pairs of the responses you want to give, where you can see the pair of responses. Then we need to create the object of the chat and pass the reflections and responses to the ELIZA chatbot using the function ELIZA chat. After that, we can create function ELIZA chatbot.converse function to set up a conversation. As you can see from this code, input text was passed and then matched against a series of regular expressions. Once the input was matched, a randomized response that sometimes echoed back a portion of the input was returned. So something such as "I need a taco" would trigger a response of "Are you sure you need a taco?" Obviously, the answer is yes, and fortunately, we have advanced to the point where technology can provide one to you. But this was still in the early days. Shockingly, some people did actually believe ELIZA was a real human. However, what about more advanced bots? How are they constructed? Surprisingly, most of the chatbots that you're likely to encounter don't use machine learning. They use what's known as retrieval-based models. This means responses are predefined according to the question and the context. The most common architecture for these bots is something called Artificial Intelligence Markup Language, AIML. AIML is an XML-based schema to represent how the bot should interact to the user's input. It's really just a more advanced version of how ELIZA works. Let's take a look at how responses are generated using AIML. First, all inputs are pre-processed to normalize them. This means that when you input "what's up," it is mapped to "what is up." This pre-processing step funnels down the myriad ways of saying the same thing into one input that can run against a single rule. Punctuation and other extraneous inputs are removed as well at this point. Once this is complete, the input is matched against the appropriate rule. I will show you a sample template. This is the basic setup, but you can also layer in wildcards, randomization, and prioritization schemes. For example, this pattern uses wildcard matching. Here, the asterisk wildcard matches one or more words before "for me" and then repeats these back in the output template. If the user were to type in "dance for me," the response would be "I'm a bot. I don't dance. Ever." As you can see, these rules don't make for anything that approximates any type of real intelligence, but there are a few tricks that strengthen the illusion. One of the better ones is the ability to generate responses conditioned to a topic. For example, here is a rule that invokes a topic. Once the topic is set, then the rules specific to that context can be matched. Let's see what this interaction looks like. "I like turtles." Then the bot would say, "I think this whole turtle thing would be a problem. What do you like about them?" Then your reply would be, "I like how they hide in their shell." Then the bot cleverly replies, "I wish, like a turtle, I could hide from this conversation." Quite a funny and sarcastic bot, right? You can see that the continuity across the conversation adds a measure of realism. You probably think that this can't be state-of-the-art in this age of deep learning, and you're right. While most bots are rule-based, the next generation of chatbots are emerging, and they are based on neural networks. In 2015, Oriol Vinyas and Kwok Le of Google published a paper which described the construction of a neural network based on sequence-to-sequence models. This type of model maps an input sequence, such as ABC, to an output sequence, such as XYZ. These inputs and outputs can be translations from one language to another, for example. However, in the case of their work here, the training data was not language translation, but rather tech support transcripts and movie dialogue. While the results from both models are both interesting, it was the interactions that were based on movie model that stole the headlines. These are sample interactions taken from the paper. None of this was explicitly encoded by humans or present in a training set as asked, and yet, looking at this, it is frighteningly like speaking with a human. However, let's see more. Note that the model responds with what appears to be knowledge of gender, he, she, of place, England, and career, player. Even questions of meaning, ethics, and morality are fair game, as you can see here. The conversation continues. If this transcript doesn't give you a slight chill of fear for the future, there's a chance you may already be some sort of AI. I wholeheartedly recommend reading the entire paper. It isn't overly technical and will definitely give you a glimpse of where this technology is headed. We talked a lot about the design of chatbots, but let's now move on to building our own. In the next video, we will build a chatbot. Hi, this is the last video of the section, Building a Chatbot. In the previous video, we designed the chatbot. In this video, we will first look at existing chatbot, then we will build our own chatbot and test it with a few questions and answer responses. Now, having seen what is possible in terms of chatbots, you most likely want to build the best, most state-of-the-art Google-level bot out there, right? Well, just put that out of your mind right now, because we will do just the opposite. We will build the best, most awful bot ever. Let me tell you why. Building a chatbot comparable to what Google built takes some serious hardware and time. You aren't going to whip up a model on your MacBook Pro that takes anything less than a month or two to run with any type of real training set. This means that you will have to rent some time on an AWS box, and not just any box. This box will need to have some heavy-duty specs and preferably be GPU-enabled. You are more than welcome to attempt such a thing. However, if your goal is just to build something very cool and engaging, I have you covered here. I should also warn you in advance. Although Cleverbot is no Tay, the conversations can get a bit salty. If you are easily offended, you may want to find a different training set. Okay, let's get started. First, as always, we need training data. Again, as always, this is the most challenging step in the process. Fortunately, I have come across an amazing repository of conversational data. The NotSoCleverbot.com site has people submit the most absurd conversations they have had with a Cleverbot. How can you ask for a better training set? Let's take a look at a sample conversation between Cleverbot and a user from the site. So this is where we'll begin. We need to download the transcripts from the site to get started. To do this, we will use the import.io extractor that we have used earlier. You can see the link. You can just go there and sign up if you want the data. You'll just need to paste the link into the form on the page. This is the site you need to use. You can just copy the URL and paste it here, and click on Try It Out. Once you click that, you'll get a page like this. Once this is submitted, the site will process the request and return a page back that looks like this. You can then click on Run URLs. From here, if everything looks right, you will see this page. The site will process and bring back the page. Next, you need to click on Show URL Generator and set the parameter here. Next, you can set the range of numbers that you'd like to download from, for example, 1 to 20, by one step. Obviously, the more pages you capture, the better this model will be. However, remember that you are taxing the server, so please be considerate. So, from 1 to 20. Once this is done, click on Add to List and hit Return in the text box, and you should be able to click on Save. It will begin running, and when it is complete, you will be able to download the data as a CSV file. Once the Save button is available, click on it, then Run URL. Once you click on Run URL, you will see that the data is being processed here. 20 URLs are run successfully in 44 seconds, and the total number of rows is 153. You can just preview the data. Once done, you can download the CSV file here. So the CSV file will be downloaded, which we can use in our system. Next, we will use our Jupyter Notebook to examine and process the data. We'll first import pandas and the Python Regular Expressions Library, RE. We will also set the option in pandas to widen our column width so that we can see the data better. You need to run this line of code. Once that is done, we will load our data. Here, I am passing the path of the CSV file that we have downloaded. I have just renamed it to NSCB. You can see that here. You can see the data here. As we're only interested in the first column, the conversation data, we'll pass this out using this line of code. This line of code will get the data from the first column up to the 0 index. In this output, we have interactions between user and Cleverbot, and that either can initiate the conversation. To get the data in the format that we need, we'll have to pass it into question and response pairs. We aren't necessarily concerned with who says what, but we are concerned with matching up each response to each question. We'll see why in a bit. Let's now perform a bit of regular expression magic on the text. So this is the line of code you need to run. Here, using the regular expression, we are finding the question and their responses. And then we are extending the QA pairs inside the CList. Let's print the convo frame. You can see the question and the response frame. Okay, there is a lot of code there. I'll explain what just happened. We just created a list to hold our question and response tuples. We then passed our conversations through a function to split them into these pairs using regular expressions. This is the function, and here we are using the regular expression. Finally, we set it all into a pandas data frame with columns labeled Q and A. We will now apply a bit of algorithmic magic to match up the closest question to the one the user inputs. This is the code you need to run. Here, we imported our TF-ID vectorization library and the cosine similarity library. We then use our training data to create a TF-ID matrix. We can now use this to transform our own new questions and measure the similarity to existing questions in our training set. Let's now get our similarity scores using this line of code. This is the cosine similarity between the question 1 asked and the top 5 closest questions. To the left is the index, and on the right is the cosine similarity. Let's take a look at these. As we can see, nothing is exactly the same, but there are definitely some similarities. For example, the word name is similar in all the datasets. Let's now take a look at the responses. This is the line of code to check the similarity of the responses. This is the output. Sean is a boy's name. Okay, so our bot seems to have an attitude already. Let's push further. Let's create a handy function so that we can test a number of statements easily. You can see that we have created a getResponse function, which is transforming the data calculating the cosine similarity, sorting the values, producing the results, and returning the answer to get the response function. Once it is done, we can use getResponse to ask questions and get the responses. So if you say, "Yes, I am clearly more clever than you will ever be," the answer is, You're George Bush? We have clearly created a monster, so we'll continue. Let's tell it, "You are a stupid machine. Why must I prove anything to you?" So it responds, "No, I didn't. But what is it anyway? I'm enjoying this. Let's keep rolling with it." I will give a few more examples. "My spirit animal is a menacing cat. What is yours?" Sean? I didn't actually name it. So this is what he has to say. "Yeah, you did." Let's continue. "Do you have a name suggestion?" "No," it says. "I think it might be a bit aggressive for a kitten." This is what it says. "Oh, I don't care. I'm still free. You can't take the sky from me." So, finally, I'll say, "And are you, Cleverbot?" So it is saying this. Quite smart. You can also form your own question. Are you a Cleverbot? So, yeah, I'll ignore that for now. In this section, we had a full tour of the chatbot landscape. It is clear that we are on the cusp of an explosion of these sorts of applications. Hopefully, this section has inspired you to create your own bot, but if not, at least perhaps you have a much richer understanding of how these applications work and how they will shape our future. This marks the end of the course. I hope you will be able to implement your own machine learning models after taking this course. I had a lot of fun with this course. I hope you had too.